looks like that. It has Q in the diagonal, and I'll explain in a second what it is. And it has P in the upper subdiagonal, it's called, I suppose. I don't remember that. Q is the probability of the stock price going down. P is just 1 minus Q. It's the probability of the stock price going up. Okay? That's one matrix that we have to define. Another matrix is just discounting matrix. That's a very simple matrix. We call it R. It has only diagonal elements. It's 1 plus the interest rate. It's the way you discount when you go backwards one period. So defining these two matrices is, of course, very, very simple. Then I can define a transition matrix, which I can call phi, which will be just R times Q. Okay. Now, we have these two matrices. We have this final array of call prices. I'll call it P, say, terminal. And the stock price is given very simply by Q max times R to the power of N times P times P. Now, it's the way you write it mathematically, but lucky enough, with Speakeasy, it's exactly the way you put it into the program. And that's it. Obviously, you can see that what we end up here is a vector. It's not one number. Well, you have to look at the first element of the vector. The first element of this vector will give you the call price. And by the way, there are a few nice things here. One is that just take a power set of matrices. The way you do it mathematically, you just write it. Q times R to the power of N. Second, I think that you never have to worry about transposing the vectors, doing it the right way. If you forgot, if you multiply from the other side, you forgot to transpose, it will do it for you. So you just write the vectors, and it will take care of the transposition. That for somebody as sloppy as I am, when it comes to matrix operation, it comes very handy sometimes. One improvement on that is that actually the matrix shrinks inside. We can reduce this matrix. We don't have to take it to the power of N. This is the phi matrix. Each time we go a step backward, we can just look at submatrix, which is 1 row and 1 column less. In other words, if we start with n by n, the next step we have to multiply only by n minus 1 times n minus 1, and forget about the last element of the vector that will multiply. So that's another operation that is relatively easy to do with Speakeasy. Kind of drop 1 column in 1 row of the matrix and keep digressing backwards. But the idea is that the whole tree structure of the binomial of the stock price behavior or the call price behavior is reduced into one simple matrix operation. And it's just this transition matrix. This one will be phi to the power of N times C sub T, the terminal prices. So that will give us the call prices. So I'll show you a few things, maybe a few graphs that we got with that. This was fairly simple. Okay, this is running the program in a loop. What we see here is what happens as we approach maturity. The straight line is a payoff at maturity, and the colorful lines converging to maturity is just the time before maturity. So the outmost line, let's see if I can point to the pointer. Yeah, this line will be 90 days away from maturity. And you can see that you can kind of shrink as the time to maturity decreases. You can shrink into this straight line, which makes sense because if look at it from a probabilistic point of view, the question is what is the probability that between now and 3 months ahead the stock will appreciate $10? Then you, let's say, have a fairly high probability, but what's the probability that between today and tomorrow the stock will appreciate $10? It's a very small probability. So that's why there's a drop in the call price, because the call price reflects the probability that you will make profit. And the probability that you will make profit goes down with time as you approach maturity. Let's define another window now, maybe, and okay. Actually, you can use X window, which is nice here to move and